Many manufacturers in the mechanical industry face the challenge of verifying the surface finish of the parts they produce. But a lack of knowledge or resources often leads to poor choices regarding the instrument, the measurement protocol, and the analysis. And those mistakes can cost money, time, and generate quality issues. This video will guide you through choosing the right instrument, interpreting technical drawings, deciding between profile and surface measurements, and selecting the right analysis methods and parameters. In just a few minutes, you'll know how to avoid the most common mistakes. Surface metrology began with contact profilometers, evolving from the first instruments in the 1940s to aerial profilers in the 1980s. International standardization unified the language of roughness by defining a shared set of tools and parameters, with early standards such as ISO 468, ISO 3274, and ISO 4287. These standards were later refined, and today profilometry remains widely used. The recent ISO 21920 standard for profiles, published in 2021, is as important as ISO 25178 for aerial measurements. It is only with the aerial standard that optical profilers have been fully integrated to the surface texture analysis workflow. All these possibilities leave a lot of possible options to users. Therefore, some of them face an important question. When is a profile measurement enough? And when is a 3D aerial analysis required? Three-dimensional metrology is not necessarily better than 2D profilometry. It depends on the context, the surface complexity, and the instrument available. Each instrument has its strengths and limitations. It must be used in the right context. Most 2D profilometers use a contact stylus with a small spherical tip of known diameter. This makes them well suited for metallic parts in mechanical and automotive industries. However, the stylus applies a local force that can sometimes scratch delicate surfaces. Another drawback is that the tip trajectory is sometimes not perfectly straight due to torsion effects and lateral pressure caused by local hills and dales of the surface. The result is that points are not sampled at the expected XY position, leading to uncertainties. In order to reduce these problems, the scanning speed is usually limited below 500 micrometers per second, making profile measurements slower. In 3D contact profilometers, multiple parallel traces are measured using a motorized Y-stage, which increases measurement time, sometimes to several hours. For more information on Stylus profilometers, see the video Introduction to Stylus Profilometers. The link is provided in the description below. This video introduces the history of Stylus profilometers, describes their design and components, explains how they work, and browse through various brands and models. Finally, it concludes by highlighting advantages and drawbacks. Historically, the first 3D profilometers were built from 2D instruments by adding a Y-stage. Parallel profiles were recorded to reconstruct a rectangular area. To overcome these speed limitations, modern scanning profilometers use single-point optical sensors. Because they are non-contact, measurements can be faster than with a stylus-based probe. These instruments are ideal for measuring large parts, as the lateral size depends on the travel of the X and Y stages. The most common probes found in these systems include chromatic confocal probes, point autofocus probes, point interferometric probes, and laser triangulation sensors. Each technology has its strengths: confocal for the ability to measure reflective surfaces, interferometry for its precision on smooth materials, and laser triangulation for fast acquisition on rougher textures. Today, modern instruments do not touch the surface but see it. Optical profilometers use a camera combined with a specific optical setup to measure heights. The field of view depends on the selected objective, but typically ranges from a few hundred micrometers to a few millimeters. The dominant technologies are white light interferometry, confocal microscopy, and focus variation microscopy. Each point's height is determined through vertical scanning. The instrument captures a stack of images while moving along the z-axis, and a reconstruction algorithm determines the height from intensity variations. This method enables fast surface acquisition with high vertical resolution. For each pixel, the recorded intensity values form a specific curve, which depends on the optical principle. In interferometry, the curve shows interference fringes. Its center defines the height. In confocal microscopy, the highest intensity peak gives the height where the point is in focus. In focus variation, the algorithm identifies the most focused point by analyzing local contrast around each pixel. The determination of height from these curves can be affected by various factors: surface reflectivity, steep slopes, or transparent layers. These may cause missing or incorrect height values, called non-measured points and outliers. Understanding and correcting these artifacts is essential to ensure meaningful results. For more details, see the video, Pre-Processing Surfaces Measured by Optical Profilers, linked in the description. This video explains how to detect and remove outliers, fill in non-measured points, and apply proper filtering to ensure reliable metrological results. The design and metrological characteristics of these instruments are described in ISO 25178, parts 601 to 607, first published between 2010 and 2019, with recent revisions in 2025. Each metrological property can be calibrated, and the impact of influence factors can be evaluated following Part 700 procedures. When verifying a surface texture specification on a technical drawing, the graphical symbol and the specified parameter help determine whether it is a profile or an aerial specification. Profile specifications can appear in two different forms depending on the standard used. The first form is the well-known root symbol, used for profile parameters defined in older standards such as ISO 4287. This symbol at least contains the parameter name and the tolerance value. This indicates that the surface must be verified by a 2D profile measurement using a contact profilometer. The second form is the modified root symbol introduced by ISO 21920 Part 1. It includes a short line segment above the left triangle. Parameters are therefore those defined in Part 2 of the same standard. Aerial specifications use a different root symbol, which includes a ROM above the left triangle, introduced in ISO 25178 Part 1. This indicates that the parameter is defined in Part 2 and must be measured using a 3D aerial profiler. For more information on surface texture indications and the root symbol, see the video, Indications of Surface Texture on Technical Drawings, linked below. This video explains how to read and interpret each part of the symbol, the 16% rule, and the default settings that are often omitted. However, how to analyze a surface when no drawing specifies what to measure. Besides the mechanical industry, many parts are not specified with technical drawings. When exploring new materials or surface treatments, users must decide which measurement type is appropriate, profile or aerial. This choice depends mainly on the complexity and isotropy of the surface. Outside traditional machining, many modern surfaces are not simple or homogeneous. Some are textured or structured to achieve a specific function, such as improving adhesion, reducing friction, or enhancing hydrophobic behavior. In such cases, the choice between a profile or an aerial measurement is directly derived from the surface complexity. We can represent the different kinds of surfaces along an axis ranging from stochastic to deterministic. A stochastic surface is random and isotropic. Its properties are the same in all directions. A deterministic surface, on the other hand, contains geometrical patterns or directionality, making it anisotropic. The more structured the surface, the more complex it becomes. Depending on their position along the complexity axis, some surfaces can be accurately analyzed using profiles, while others require aerial measurements. Let's see some example surfaces with various complexity. This first example shows a homogeneous, isotropic surface, meaning it has no visible directionality. When profiles are extracted in different directions and analyzed, the roughness parameter, for example RQ, remains almost constant regardless of the measurement direction. In this case, a 2D profilometer provides reliable results, and using a 3D optical profiler brings no added value. This second surface shows parallel grooves, typical of machining processes such as grinding or brushing. Profiles measured perpendicular to the grooves give stable and representative roughness values. However, profiles measured at an angle or along the grooves produce smaller or inconsistent results. In such cases, the direction of measurement must be carefully selected, always perpendicular to the texture lay. This direction is sometimes indicated on the technical drawing. Some surfaces are slightly heterogeneous, showing local variations in texture or composition. In these cases, a single profile cannot represent the entire surface accurately. The measurement must therefore be extended to a larger area using an aerial profiler, so that spatial variations and local features can be fully characterized. Ultimately, though, it is possible to stabilize parameter values by measuring many profiles at different positions and orientations. When heterogeneity becomes too large, parameter values differ significantly, so the surface can no longer be measured reliably using profiles. It is then necessary to measure aerial surfaces. Highly structured or patterned surfaces, such as those created by laser texturing, 3D printing, or electrical discharge machining, are deterministic and require aerial measurements. Their function often depends on periodic structures or orientation effects that cannot be captured with 2D profiles alone. Each manufacturing process creates a specific surface, like a signature that is characterized by its own complexity and isotropy. For example, turning, grinding, or polishing usually produce simple, directional surfaces. In contrast, electrical discharge machining, brushing, additive manufacturing, or laser texturing generate more complex and often anisotropic surfaces. Each material, each process is associated with a specific surface topography, with its own complexity. Stochastic surfaces, such as sandblasted metals or rough coatings, exhibit random roughness. Their texture is homogeneous and properties are similar in every direction. In this case, a 2D profile measurement can provide representative parameters, as any profile will statistically reflect the overall surface behavior. Classical height parameters are suitable. Between stochastic and deterministic surfaces, there are hybrid textures, heterogeneous or with partial directionality. Brushed metals or rolled sheets, for instance, show anisotropy but still contain random roughness at smaller scales. Here, both profile and aerial measurements can be used, depending on the analysis purpose. 3D measurements help to better capture the directional component. In case of profile measures, it is wise to stabilize results by averaging several measurements. Deterministic surfaces are fully structured or patterned to achieve a functional purpose. Examples include micro-dimples for lubrication, micropilers for friction reduction, or laser-created textures for hydrophobic behavior. These surfaces must always be measured and analyzed in 3D, since their geometry cannot be captured by a single profile. To summarize, there are two main cases. If you have a drawing with a specification, then everything is deduced from the root symbol, its indications and default specifications. Or you explore a new surface in order to understand its properties. Here, the complexity of the surface guides you on the type of instrument and the analysis. An aerial analysis can always generate profiles by extraction from a surface, but a 2D profilometer will never correctly analyze complex surfaces. Aerial measurements are essential for complex, anisotropic, or with functional structures. These surfaces are more and more common in modern engineering as well as in nature. The correct analysis of surface texture requires both technical understanding and metrological rigor. Before measuring, always define the goal. Are you verifying a specification or exploring a new material? Choose the instrument and parameters accordingly, note the measuring conditions, and interpret the results with regards to the surface function. And remember, a meaningful measurement starts with a meaningful question. Understanding a surface means understanding the process that created it, or the circumstances that modified it. Thank you for watching this video. Feel free to comment and indicate your needs for future videos. Click on the like button below this video and subscribe to the channel to be notified when new videos are uploaded. You will find other resources in the Surface Metrology Guide. You can also visit www.digitalsurf.com to learn more about mountain software. Thank you.